Good morning. We are Team 4, and our capstone project consisted of redesigning the Blair Street Pier in Alpena, Michigan. This project was an MDOT partnering project. Our team consisted of myself, Dylan Reynolds, and my focus was on the construction project management aspect of things.
And I'm Alex Bliss. I handle the geotechnical and foundation design.
I'm Paul Poor. I also assisted in the geotechnical and foundational design.
My name is Kyle Getchell, and I am doing the structural engineering aspect.
This team was also assisted by our sponsor, Dustin Black of Michigan Department of Transportation, and our faculty advisors, Dr. Haynes, Dr. Hu, and Dr. Shao. And we'd also like to thank them for their guidance and feedback throughout this project. So to give a little bit of background on our project in the Blair Street Pier, it is located in Alpena, Michigan, along the shore of Lake Huron. And due to rising water levels, the pier has been battered by Lake Huron. This has led to a deteriorating wooden superstructure. And because of this, the city of Alpena had to close the pier down in 2020 and completely barricade it in 2021. The pier is 14 foot wide and extends roughly 350 feet into Lake Huron. Here we just want to showcase an overview of the pier and give a highlighted location of Alpena County to help give a geographical location for our project. The two pictures here display the current conditions of the Blair Street Pier. Lake Huron has clearly taken its toll on the pier and park, and this is shown by the substantial amount of erosion and destruction due to the rising water levels. And this should help exemplify the importance of this project moving forward. The mindset we wanted to implement when approaching this project was that we wanted to create a design that reflected the blue-collar roots of a timber and sawmilling community, which Alpena is. With that being said, our technical challenges involved maintaining the same footprint and increasing the elevation of the superstructure while maintaining a serviceability of L over 360. So moving on to our deliverables, we had our United States Army Corps of Engineers permit application, a superstructure design, pile design, which included 4 alternatives, an analysis of each of those pile alternatives, our pier scour analysis, and an engineer's cost estimate. So our Army Corps of Engineers permit application is shown here. These permits are necessary for any work, including construction and dredging in the nation's navigable waters. The review process for this analyzes the benefits and detriments of the given project. And ours having no cut, fill, or discharge, we didn't see this having an issue being approved or accepted.
Based on our selected members, we calculated our dead load to be about 14.5 pounds per square foot. And we decided to round this up to 20 pounds per square foot based on recommendations from our sponsor due to fasteners and other miscellaneous connections that we did not include in our project scope. Using AASHTO's LRFD guide specifications for pedestrian bridges, our design needed to support a live load of 90 pounds per square foot. We also used ASCE 7-16 to determine our snow load of 37 pounds per square foot. Using a load combination 2, our overall load on the structure is 187 pounds per square foot. We at first envisioned large timber girders that we were able to eliminate by reconfiguring the load path. Using a one-way slab system, we got a distributive load of 238 pounds per foot, acting on the joists as seen in the top figure. These joists are sitting on top of the transverse beams, which creates point loads as seen in the bottom figure. We then determined that each pile must support a load of 18,000 pounds. Using SAP and completing verification calculations, we found the moment and shear of the joists to be about 5,700 foot-pounds and 1,600 pounds respectively. Inside joist is controlling, and it'll be sufficient for the outside joist as well. This allows us to use the same size material and reduce any mistakes during construction. Based on the results, we decided to use a 3 1/8 by 9 inch glue lam which satisfies our requirements. Our next step was to check the deflection of our selected joist member. MDOT's bridge design manual requires a live load deflection to be less than L/360 for pedestrian piers. We used SAP 2000 to analyze the joist and found the deflection to be about 0.28 inches. To verify we got the correct answer using SAP, we wanted to complete verification calculations by using the equation shown on the left there, which confirmed our analysis was correct. The actual deflection was well below the maximum allowable deflection, which was almost a ½ inch. Using SAT, we also determined the moment to be 64,000 foot-pounds and the shear to be 18,000 pounds on the beam. Based on Boise Cascade's manufacturer guide, we had several options to choose from, but we ended up deciding to use a 6 3/4 by 18-inch glulam for design based on the cost per linear foot, which we will discuss in a little bit here. Since our deflection is based on the live load, we had to determine the live load that acted on the transverse beam. This is the same process we used to calculate the total load on the pier. We assumed a pin and roller support since the connections were beyond the scope of our project. We then used SAP to analyze this beam, which gave us a deflection of 0.18 inches, which it's safe to say that our beam won't fail under deflection. Our design process consisted of making assumptions for our loads at first to get started. Once we determined our materials, we were able to get an accurate dead load calculation, and then we reiterated that process to get our final design. This is a visual representation of the joist sitting on top of the transverse beams, which then transfers the load to each pile on the far ends. Our design consisted of 3 2x6 decking boards that are equally spaced along each post in the vertical direction. The railing posts are then spaced at 4.67 feet in the longitudinal direction. We also designed our pier in 14-foot sections to allow us to make any changes seamlessly.
And now we take on the geotechnical and foundation design. To the right, you'll see a summary of the process of this design, which we will be diving into. In beginning the investigation, we found we had a limited amount of site information at our disposal. In fact, the only useful information we could gather were soil borings from 1957 that only offered soil descriptions and not classifications. This proved to be significant because almost every value had to be assumed from this point on and found through prior studies that reflected the soil descriptions we have. We ultimately decided that we would remove the existing sheet piling and start anew. And moving forward, we would consider several types of piles, which begins our alternatives of analysis. And as Kyle stated earlier, an 18.3 kip downward load acts on each pile. And to design a pile to handle this load, we had to determine the toe bearing and side friction resistance the pile experiences. We are most interested in the depth where the pile is experiencing 18.3 kips. And it should be noted all equations come from the 3rd edition Foundation Design textbook authored by Kudito. And based on the soil descriptions, we divide the soil profile into 3 sections as shown in the table. Here you will see important characteristics of each soil classification we identified. And these soil classifications are based off of ASTM D2487. We classified the top layer as a well-graded sand, the middle layer a low plasticity clay, and the bottom a dense silty sand. A standard penetration test was requested to gather more information. The SPT yields N values, which are adjusted using an overburden correction that compensates for effects of effective stress, which then allows us to determine the modulus of elasticity. The N values were determined through the soil classification and the level of firmness gathered from the soil description. In the bottom portion of the table, you'll see my rationale for determining the factors in the correction equation. And this brings us to the side friction analysis, a very involved process. This equation presents several factors which were easily determined for the cohesion of the soils. However, for the clay, it was a bit more difficult to determine those factors. Hence the beta method. Because the factors were difficult to determine for the clay, through use of the beta method, we were able to combine all those factors into a single factor, beta, and fortunately enough, we could rely on studies such as Meyerhoff, who determined a loose clay will have a beta value of 0.2. And this will bring us to the result of our side friction, which are presented in the corners. You'll notice the different depth is associated with each pile, and that is due to the depth where the 18.3 kip load was reached.
Equation 13.5 is our team's main equation that was used. Pn is the nominal downward load capacity. Equation 15.1 was used in our two cohesionless soil layers. Q prime n is the nominal net toe bearing net capacity. Equation 15.6 was used in our single cohesionless soil layer. We assumed undrained conditions existed in our cohesive soil layer beneath the pile toe. The NC asterisk there was also assumed to normally be 9.0. The cohesive soil layer generated a very small portion of the load capacity from the toe bearing. And equation 15.2 is our rigidity index. Here we have the equations specific for each pile. The AS equation at the top comes from the equation P equals PPN, where PN is equal to FY times AS. This allowed the team to compare and select an H pile based on the cross-sectional areas with that in the tables from our foundations book. The axial compression equation was used in determining which timber pile to use. Here the P was our 18.3 kips found earlier from Kyle. Equation 18.3 was used in determining the specs for helical pile. The difference here is the AP and the AR terms. These represent area of plate and the area of the rod. Through all the calculations the team provided, the steel HB 8x36 piles toe bearing reached a PN of 18.3 kips or higher at a depth of 28 feet. This yielded a toe bearing of 53.2 kips per foot squared. The same calculations were completed for the helical pile. The pile provided a low depth of 6 feet until PN greater than or equal to 18.3 kips was met. The toe bearing at this depth was 47.8 kips per foot squared. The same calculations were also completed for the steel pipe pile and the treated timber pile. The treated timber pile provided a low depth of 6 feet as well, with a toe bearing of 49.1 kips per foot squared. The steel pipe pile provided a depth of 25 feet and the toe bearing of 46.9 kips per foot squared at that depth. Here we have the toe bearing results in a nice table format. We can see that the helical and treated timber piles have a low depth of 6 feet. However, these will be driven until resistance is met. The solid diameter of the treated timber piles also has a direct effect on the toe bearings. The higher the cross-sectional areas, the higher the toe bearings will be.
Next, that brings us to our analysis of alternatives. In order to do an analysis of alternatives, we first had to select criteria in which the owner valued the most on the project. We selected design cost, constructability, aesthetics, and sustainability. We then met with the owner to determine how important each of them was. We rated them as design cost 2, constructability 3, aesthetics 4, and sustainability 2. This means aesthetics was valued twice as much as sustainability. From there in our analysis process, we scored each alternative on a scale of 1 to 10, 10 being the best score and 1 being the worst. Once we completed this analysis, we multiplied these scores by the weights given from the owner to get our weighted scores. Timber having a total score of 82 as the highest implies that based on the preference of the owner, timber piles should be selected.
For our Pier score analysis, we used the Federal Highway Administration's hydraulic toolbox program. We selected a circular cylinder shape with a plain bed flow, or plain bed and anti-dune flow. Our depth and velocity were determined using NOAA's nautical chart and currents map. We made conservative estimates to ensure the worst possible scenario. Our width and length of the pier were 10 inches with an angle of attack of 90 degrees plus a 10-degree angle of the pier itself. With that data, we determined our scour depth to be 0.043 feet with a scour hole bottom width to be 0.083 feet and a scour hole top width to be 0.87 feet. To show how our scour changes with respect to water depth, we decided to use a smaller water depth of 5 feet and keep the other variables the same. The scour depth reduced to 0.39 feet, the scour hole top and bottom width to 0.083 feet. Our results show that there's a linear relationship between the water depth, scour depth, and scour hole width.
Next, we will go into our estimate. To start, we highlighted 9 major construction tasks for this project. The Gantt chart shown here is for timber, and this allowed us to get an idea of the project duration, in turn allowing us to estimate our labor costs. For the estimate, Boise Cascade was the manufacturer, and First Source was the supplier for the superstructure. The superstructure was broken up into the beam and joists, the decking boards, and then the railing posts. For the substructure, the MDOT foundations and piling pricing table was used. The substructure was broken up into pile costs, driving costs, and setup. So breaking down our cost estimate, we have our superstructure, which came out to about $115,000. Our substructure came out to about $54,000. Our labor costs came out to about $57,000, and our traffic control was $10,000. We totaled these up to get our first subtotal. We then used 10% mobilization costs to get roughly $23,000. We added this into the initial subtotal to get a second subtotal. We then took 10% for our contingency costs, which came out just below $26,000. And then we added each of these up to get a total project cost of $284,000.
Timber is a sustainable and renewable resource, provided that responsible forest practices are used. Timber also does not need to be imported from other countries. As you can see, Alpena is known for their industrial logging pass. This photo shows Fletcher Paper Mill from 1908 in Alpena. And these are the types of things that are considered in NEPA studies. For our pier scour analysis, the sedimentation of eroded materials can cause many environmental issues in conjunction with compromising the structural integrity of the pier.
So now for our summary and recommendations of the owner. The first thing we'd recommend is to get new soil borings. The soil borings, as we stated, were from 1957, and being over 60 years old, we believe it would be beneficial to get these updated and in locations that the pier is going to be rebuilt. And based on our analysis of alternatives, we'd recommend the owner uses the timber pile, and they also raise the elevation 5 feet from the existing elevation of 583.5 feet to the proposed elevation of 588.5 feet. And we want to include that our design for this did include this elevation raise. Does anybody have any questions?
Industry Advisory Board members, I'm sure we've got some questions.
This is John. Was there any thought of how the construction is going to go on this thing? What the drawbacks? What are they going to run into with this? I know you're ordering extra soil borings, and that's a wonderful thing. But how are they going to build this? In your thought?
So in our estimate, we included a barge essentially for the machinery to be operated on. And once you get the piles going and you start getting the beams and joists on there, it's basically going to be a safety factor for the company of just making sure people are safe when they build the decking. And once you extend out, it's going to be obviously safer because you have the decking and everything going for you. But basically this included a barge for the crane to operate on to drive the pile. And we did include that in all of our estimates and the time frame for mobilization and the driving time.
How was the ice flow brought into this design? I mean, was there any? I mean, I didn't remember seeing any. But what about ice?
We did determine, calculate in our, we took into account ice. We did some calculations on that, and that was going to be, we determined, I think it was about 6 pounds per square foot that would be on the structure during the winter. That was kind of, I think we took that into account with our dead load too. We added a little extra to our dead load, and then with our load combination, that could also be taken into account for that. But it was pretty minimal based on what we found out. And that was using ASCE 7-16.
Great. Nice job.
Thank you.
Thank you.
Hi, this is Bill in Alpena. I had a question. Did you take into account the approach to the structure, the connection details to the parking area, accessibility, given the grade change?
So that was outside of the scope of the design of the pier itself. Basically, we just would assume that the steps would be added, and this would require a new site layout for the park itself. But having it barricaded off and completely shut down right now, we're assuming that's going to have to happen anyways. So in terms of connecting the pier to the park, that is going to, we assume, outside of our scope of work and site design layout.
Yeah, and to piggyback on Dylan's reply, part of our constraints was maintaining the original footprint. So we would try not to make too many changes to the grade of that parking lot if possible, given that this is a record level year for water levels. And if you look at the Army Corps data, you'll see for, I believe, 2020, January through August were all record months for water elevations.
Thanks very much.
Does the end of the pier slope down to get it near the same elevation?
No, we didn't take anything like that into account. We wanted it to be raised because of the water levels currently are what's destroying it. So we wanted it to be above the current elevation.
Yep, that makes perfect sense. Just when you talked about 5-foot elevation, I thought that's interesting. It would just, besides the steps, you'd always have to take into account, I think, the ADA concerns.
Mm-hmm.
So that about an 8% of 1 on 12 at 5 foot gives you about an additional at least 60 foot of ramp you're talking about. So that, that's just, it's always an interesting thing, something like this that's a feature. The aesthetic concerns are certainly important. The 60 foot might be an interesting amount of real estate for the footprint of the park. Just thought I'd make the point.
Yeah, thank you
very much, though. It's an excellent presentation.
We appreciate your feedback.
I have some questions about any environmental impacts that were considered. So to your constructability, was there any restrictions on work that could be done in the water, maybe based on the habitat restrictions? Maybe found that through your permitting process, or if you had to add into your cost estimate additional items for turbidity curtain or any kind of erosion concerns.
So to go, I guess, first on the environmental aspect of that, It is currently all completely sheeted off. It is, I'm drawing a blank on what it's called, but it's basically just steel sheeting. Is how they have it built currently. So in terms of driving these piles, it could essentially just be drilled inside of that sheeting for how it stands currently. Moving forward, sorry, I'm drawing a blank on the next part of the question.
Just again, you're kind of answering it with it sounds like there's a coffer dam in place. So it's kind of any kind of sediment that would be disturbed would be contained in that area. But I just wondered if you guys considered any of that.
Yeah, and to answer your question about the erosion, Dylan, if you wouldn't mind going to that current state slide of the park. As you could see in the current state, like the water has washed up and really like pulled some of the parking lot away, and you can see that concrete bench has been pulled away. Our sponsor presented us with another project that we could have taken where we would be reinforcing the shore to battle the erosion issue. That ultimately was outside of our scope for this project, but it is a very valid point to bring forward with this last year being a record level year for water elevations.
Any other questions for Team 4 here on the Alpena Blair Street Pier Redesign project?
Are there any requirements to pull out the existing piles? I mean, how you work with the debris if you have to remove this?
There's currently no, like I said in the last answer, there is no piles for it. It's all built on steel sheeting. So those basically you just have to remove with some sort of excavator. You just chain them up and pull them straight out of the ground. So I don't know if that answers your question, but there currently is no piling for this pier.
The sheet piling acts as the main foundation component of the pier.
Okay.
And with that, we'll get ready for our 11 o'clock presentation, the Medical Service Facility Site Development in Portage. Got about 2 minutes until that one will start. So we need to take a break real quick. Please do so. Then Team 5, you can go ahead and share your screen, and then I'll give you the go-ahead as we hit 11 o'clock. So we'll stand by for a short break. 11 o'clock, we'll pick up.